So this one's quite a difficult question because what we've got is the direction of the P wave is longitudinal and it's in this direction. However, the rock must move in the opposite direction, and this is to do with Newton's idea that for every action there is an opposite and equal reaction. So if the P wave is causing a push that way, it's going to cause an opposite push on the rock. Okay, it's quite a tricky concept. Now this one, the bottom question is about why do the tectonic plates move, and it's all to do with this idea that the mantle, one of the sections of the earth, is really, really hot. Okay, and so the mantle, where it's hot, it rises, and then where it's cool, it comes back down. Now this is called a convection current. Okay, so this is called a convection current. And basically, the movement of the hot going up and the cool going back down causes the tectonic plates to rub past each other. It causes a build-up in friction, and eventually the tectonic plates move, and that causes an earthquake. Pause. Okay, very easy question here. Raging Martians invaded Venus using X-rays, guns. Right, so state which of the wave can be split into different colors. That's visible light. They can be split into red, orange, yellow, green, blue, indigo, violet. Richard of York gave battle in vain. That's how you remember that. Richard of York gave battle in vain. State which type of wave has the longest wavelength. The longest wavelength is radio waves. Which one type that has that is ionizing. You could have had any of these three: gamma, X-rays, or ultraviolet. The one with a high frequency wavelength. So gamma, X-rays, or ultraviolet. Okay, these three can mutate your genes and cause you cancer. So they are ionizing. Okay, they can mutate your genes and cause cancer. These three in particular. Okay, brilliant. So this top question here is saying, why do all the electromagnetic spectrum travel at the same time to travel to the Earth? The reason is because they all travel at the same speed, and they all travel in a vacuum. And like I said in the previous video, again, these are all the same question. The speed of light is 300 million meters per second, which is the same as saying 3 times 10 to the power 8 meters per second. Okay, so it's 300 million, which is the same as saying 3 times 10 to the power 8. That's 300 with 6 zeros at the end. So 300, 1, 2, 3, 4, 5, 6, 300 million meters every single second, which is amazing. Now, the other thing is, this is true when traveling in a vacuum. Okay, and a vacuum is something, it's spelled like this right here, is vacuum. And it's something that has Maya, what's a vacuum?
A vacuum?
Yeah. What's a vacuum? What does it do?
It sucks things up.
Oh, it sucks things up. Well, there's a different type of vacuum, did you know? It's in space, and basically it's where there's no particles at all. So there's no...
Space?
Yeah, space.
Can you show me?
I'll show you, okay, later. Is that okay?
Can you show me now?
No, sorry. Okay, so just pausing the video for a little bit. Okay, so for this question here,
Do you know
yeah.
You can put
So if you look at this here, I've just written it here. I've seen people use this method in an exam. I can't remember who it was, but it was one of my year 10 students last year. So it's one of you guys last year, if I had, yeah. But I can't remember who did it, but it's really good. And now, so I'm talking to myself, baby, just like I usually do in my lessons. I'm joking. Anyway, I'm doing this little bit of work. Is that okay, my baby?
Yeah.
Thank you. So, if you have a look here, this is the longest wavelength, but they want you to relate it to its frequency. So this one...
To your phone?
Yeah, I am. Yeah, I am. So this frequency here is a longer, or is a... The frequency here is much shorter. Right? It's a higher frequency. It's a higher frequency here and a lower frequency there because of the wavelengths. Right. So high frequency, low frequency. and then we can relate them. So that would be your mark there. Then what I'll do is I'll talk about infrared. So infrared is used for heating things. If you get too much infrared on you, it's going to heat your cells, could cause burns. Okay, so also infrared is like things like heating hot cookers, heat from radiators, really hot water, that kind of stuff. Ultraviolet, on the other hand, is from the sun. Now this is high frequency wavelength, so this is going to cause cancer. It's going to mutate DNA, cause cancer. What else? If it's reflecting off white surfaces and it's a lot goes into your eye, it can damage your lens, make your lens cloudy, therefore mess up your vision. So harmful effects. So we're looking at harmful effects and we've related them to their frequency. So that's it. Cancer, eye damage, overheating, burns, scalding, hot. Done. Okay, so here we've got a cost of electricity question. However, you need to pay close attention to the units. They've given you kilowatt hours. So what that means, they've multiplied the power, which is supposed to be in kilowatts for this equation, and they've multiplied it by the time already. So they've already done this part of the equation for you. Cost of electricity equals power times time. They've already done this part for you because it's in kilowatt hours. And then you got to multiply it by the cost. So you got to be careful here. You got to always look at the units. So they've told you that this is the units. This is the amount of power that's being used between these two times. So this was point A in time. This was point B in time. So what's the cost? So first you got to work out the difference in the amount of energy used. So this was what we finished with. This is what we started with. And this gives you a difference of 60 kilowatts. So from here to here, they've only used 60 kilowatts of power. And so that's what we've got. Our power times time is 60 kilowatt hours because it's power is kilowatts multiplied by times is kilowatt hours. So they've used 60 kilowatt hours, and each one they tell you up here costs 20p. And so you multiply it by 20p, and that gives you 12,000. Well, 1,012. What the heck? Can't read numbers now. 1,200 pence. Yeah, which is £12 if you wanted to, but you can keep it in pence. That's no problem. And now here they say the time between these two readings up here was 15 hours. Calculate the average power supplied. So in other words, between these two times they got 60 kilowatt hours of power, and that was over 15 hours. So to work out how much they got roughly in 1 hour, you do 60 kilowatt hours divided by 15. 60 kilowatt hours divided by your 15 hours. So on average, each hour they got about 4 kilowatts of power. So I'll just go through that one, because if that one comes up, it's not difficult, but you need to units. It's all about units, which is why us teachers go mental about units. If you understand the units, this is really, really easy. My camera's just it's autofocus off or something. Yeah, okay, that's better. Okay, so anyway, what's a step-up transformer for? With a step-up transformer, it uses this equation here: power equals voltage times current. I stands for current. Now, what you can have, hang on, Amaya, I'll be with you in a bit. What you can have is you can have a high voltage. And so if you've got a high voltage, you can have a low current. Now you want a low current when you're transferring the electricity through the pylons. The reason for this is if you have a low current, you end up wasting less heat energy, which means that as you're taking electricity across the national grid, you're actually wasting less energy. And so if you're wasting less energy, you're going to have more energy available for homes, because you're losing less heat energy. So that's why you have a step-up transformer. You increase the voltage, which is good. You decrease the current. Why do you decrease the current? So that you lose less heat and you make the energy transfer to homes and buildings much better. Now, once you go along the national grid, you come from a step-up transformer to a step-down transformer. A step-down transformer does the exact opposite. It decreases the voltage and increases the current, so that it can be delivered to homes, because you don't want really high voltage going into your home. It'll just fry your home. So that's going to be decreased, and the current will be increased, and that will be effective for businesses and homes. And yeah, that was quite cool. Anyway, Next page. Oh my days, are you serious? This is what check out my daughter's video. Check out Amaya's video. Remember we made a generator yesterday? Yeah. And so basically, move the magnet faster, increase the number of coils, use an iron core, increase the number of coils, move it faster, use an iron core.
And make it going faster.
Yeah, absolutely, Amaya. You tell them. And that's it, really. So, more coils, stronger magnet, move the magnet faster.
Make the magnet spin.
Yeah, make the magnet spin faster or move faster. Use a stronger magnet, more coils of wire, and that'll induce more current, really, and an iron core. So let's write that down. We'll be back in 1 second. So here it is. You use an iron core, you increase the number of coils, you use a stronger magnet, you increase the speed at which the magnet is moving in and out, because this diagram showing it's moving in and out, and all of this is going to increase your induced current, so you're going to have a bigger current happening.
My 6-year-old student.
Yeah, whatever you said, I agree. Okay, that's it, and that's 2 exam papers done.
You said 6-year-old student.
Oh, you
And
did.
that's Freya?
But he has not 6.